Hi, let's see if we can solve another tutorial on a gate level simulation and timing analyzer to see better how it works. All right. For example, let's imagine that we are going to simulate the typical MOOCs 8 already designed in P3 from the steps 1 down to 4. Down to a functional simulation, so it works and we know the structure and everything of the circuit. So now let's imagine that the next objective in this project is to solve the question, which is the maximum speed of the circuit when synthesized, for example, in a cyclone 4 FPGA. As you can imagine, the flowchart is, as usual, specify, plan, develop, and functional simulation first of all, as it was solved in the MOOCs 8. And remember, that is going to be the location, P3, learning materials on the plan C2, because the objective of the P3 project was both learn about, you may say, arithmetic circuits in Radix 2, and as well learning about how to invent a circuit that is going to be based on a hierarchy of components and signals. So the 1, 2, 3, 4 is what you've got already solved in the learning materials section in P3. From there you will find the tutorial and all the files required. So we will solve that 1, 2, 3, 4, very fast, and we will pay attention to the new thing, which is the gate level simulation and timing analyzer, to answer the question posed in this project. All right. So the first thing to do is to specify. So let's move to the corresponding folder of this tutorial where we can find the files. And so this is digsys webpage. We have to go down P3. Here in P3, you've got the idea of multiple file hierarchical structural design in VHDL. So you click P3, and in P3, it is about the design of an 8-bit adder or something like that. But before starting to solve this adder, here that in the learning materials, you have something like the method of decoders and the method of multiplexers. And here you are, the specific example that was also solved in the lab session number 4, the MOOCs 8. So this is where the project now is located. Click here and you go straight to the point. The MOOCs 8, which is, by the way, a real chip, the 74HCT181. But now let's solve it using the plan C2, because remember, we have solved it previously using plan A's and plan B. So now this is the picture of the circuit. It works like this table, selecting a given channel if the circuit is enabled. And this is an example of timing diagram that is later going to be translated into a test bench, considering the constant mean pulse to be, for example, 25 microseconds. So that is an example of outputs that you expect from the test bench. Right. So here it is next, the planning. This is the way we have invented it. The picture 2. This is the way in which we pretend to invent the circuit, and in some way, this is also answering the question that you've got in the concept map. How to expand multiplexers, how to expand the MOOCs 4 to get the MOOCs 8. Like this. This is a kind of a picture that you've got here. So we can go down here and straight, because this is already invented, and perfectly well annotated, every single signal and component. That. Let me insist. Do not go to the next section, which is developing the circuit, if you haven't got previously the plan completely annotated and clear in paper and in your mind, right? That is what is required. So now we are going to start the developing, right? Okay, so you see in this tutorial we have gone very fast from the specifications to the planning And now we are starting the development, which is going to consist of, moving the files and saving the files as with the same names in the position or in the folder where the project is going to be located. So let's save all the files belonging to this structure. Save the link as. You know that you have to go to your unit L, CSD L, and because this is a gate level simulation, you may consider that a project in P4. So new folder, it's going to be a project in P4, MUX 8, and C2, for example, because this is the plan. The MUX 8 is the chip. So, but in P4, because what are you pretending is to study the timing of the circuit. So here is a good location. The name is the same, save, and now the same for this component, save the link as the MUX 2, and the same for the MUX 4, save the link as the same way. Remember that later on we can copy as well some items from the test bench, but this is going to be later. Now let's synthesize the circuit, because we are liking to get a picture like this, okay? The one that you see here in picture 3. So this is what we are waiting for now in this synthesizing process, okay? So let's go and synthesize. I will do that in one step. So in the end, you will see the RTL just next. Okay, so, right, the project has been, a new wizard. The project has been synthesized, and so it's time for watching the netlist viewer, because we have this idea now in mind, comparing the picture that we've got from the machine, that this RTL is going to be compared with the one that you have in your paper. That's the point. The one that you have in your paper is exactly that one here, right? So just keep an eye on this picture, and now keep an eye on that picture, which is the RTL. It looks pretty right. You see, you have annotations of the wires, you have annotations of the blocks, chip 1, chip 2, chip 3, so it looks fine. It looks as if it has to work. So now it's the time for testing this thing functionally. You can go inside every single block and go back to the top and move around this, and you can just generate a picture of this, with the snipping tools, and make annotations, okay? Well, this is what you have to do in your report. You have to take a picture of this RTL and annotate it. And not now, because we are going to go farther away down to the gate level, but now is the point when you have to annotate that, right? And to tell that this is, to tell me that this is okay? And it may work as expected, as we will see now in the next idea, which is the functional test bench. The functional simulation is not complicated, It is going to consist of the pile of PHDL files that conform the hierarchy that you are inventing, and a test bench that you will get from the web, the template from the web, and you will adapt. That's the idea of the functional simulation. So let me solve it, and let me show you the results. So you have to go to processing and start, a test bench skeleton. That test bench template writer is for you the key point, because it's going to be about converting the unit and the test and everything into VHDL. So that has been right. So now is your time to move the file in the simulation, okay? And then going back to the web and replace the empty processes with the ones that you've got as example in the web page, right? So go to simulation, model sim, and take the one which is of your interest, which is the Muxate BHT, Control C, and place it rightly in the folder, paste, and now change the name of this as to be test bench Muxate underscore TV, and now change the file extension BHT. We do that all the time, so no problem, as usual. So now you've got the file that has to be added as it is to the model sim simulation. All right, so let's go back to the model sim and let's say add to project an existing file, which is going to be that one TV. Open. Okay, they both, the all four of them has been identified, has been now inputted into the project. So now it's time to run the compilation process and to see that everything is all right. But you know the test bench is empty. So now is your turn to go and modify that file conveniently. So for example, you know that after the component, you better go to the web, inspect the file, and copy the idea of the constant that will represent the time. So place the constant here. 25 means that, for example, you need to run the simulator for 300 microseconds or something similar, enough time to run the vectors. And now it's time for you to delete the init and the always and make room to place the ones that you are copying from the web. So for example, the full test bench that you've got it here, Control C, the full process can be pasted here. And now you've got, in this way, some stimulus for the channels. You see, for example, you see here that you are selecting the channel 1 and setting channel 1 to 0, and then setting channel 1 to 1 and waiting for a while before setting another channel. So this is a kind of a stimulus very similar to the one that you have in mind, which is this picture, right? This is the picture that you go simulating now. Okay, so now it's time to recompile it all here in this. Let's save it, save the changes, right? And now, let's see if the question mark goes interpreted correctly. Compile all. All right, so now let's simulate. And let's start a simulation, a functional one. And let's see the results directly. So the wave has been laid out and the signals arranged with a given divider to separate the outputs from the inputs and make the diagram clear. So now it's time for simulating. So this is run 400 microseconds, and now it's time for selecting the wave and zooming it all. So in the end, it has to work in some way or another, right? And so, for example, here you are selecting, you can change that to be in radix unsigned. So here you are selecting the channel 2, and the channel 2 is a 1, so the channel 2 is captured. That's the way it works, okay? You can add more time, run 400 microseconds, and now you can zoom all, and you have more vectors now, you see? So that's a functional simulation, and that's another end, which means that you can capture this picture and annotate it so with your text. So you are going to, tune this image so that it is understood, that you understand which has been the result from the simulation, okay? And you can do that very well. So in the end, your picture is going to look like that one that you see in the picture 4 in the tutorial, okay? Something like this. So we have finished the functional simulation. Everything was right. So now let's go to the next gate level simulation. That's the purpose of this tutorial. But you know, I go like that because I would like you to emphasize that the important thing is to go step by step. Do not attempt to solve a gate level simulation without having gone through the previous 1, 2, 3, 4 steps, because it is necessary that everything to be in place, because now the only thing for you is to add simply another simulation that has to give you perfectly well the same results, because you are going to use the same test bench. All right, so right, in order to start the gate level simulation, you have to process, you have to start the processing of the, the translation of the technology view into a VHDL file. But this technology view in some way is special and has the special extension VHO, right? And you know that this VHO is also associated to the delay file that accompanies the FPGA, which is the target chip of this project. So before starting the writing of the net list for this technology view, it is good to see what is that we are going to simulate. So go to Tools and the chip netlist viewers, and instead of the RTL now, let's inspect the technology map viewer. This is the circuit that you are going to implement. You see a lot of buffers that connects the inputs to the internal signals of the FPGA, inputs and output buffers, but apart from that, you've got the chip, and the chip now is going to be organized using the logic cell that is going to be available in the FPGA, and the logic cell is a LUTI, a lookup table. So every one of the lookup tables are organizing a given equation. So all the equations together using this network of connections generate the output. All right, so this is the circuit that is the real one. It is a flat circuit, everything like that. And this flat circuit has to be translated to a VHO file for this specific library belonging to the FPGA, right? So this is what you are going to do now. Processing, start, and EDA netlist writer. When you do that, the machine will generate all the necessary files, and those files are going to appear here. For example, this is the standard output file associated to the delays, SDO, and you've got as well the MUX8 VHO. Those two files are the ones that are going to be associated. These two files here, the VHO and the SDO, are the ones that are going to be simulated together along with the previous test bench. So this is the architecture that is the real one to be simulated by means of this tool, a gate level simulation, right? And remember that to get these two files generated, there is something tricky that may happen to you. You have to go and select the project and go to settings, and be sure that in EDA tool settings, the simulation settings, and the more EDA netlist writer settings that you see here, all are set off. All right, so be careful, because one of them, it's precisely the generate function simulated netlist, perhaps is on. So just switch it off. All right, all of them off. So in this way, you are going to be sure that everything is all right. So if everything is all right, I mean that you've got the SDO and the VHO, this time we will leave them where they are. They are in the simulation model sim folder. So we will leave them there, and we will go and tool run you see, this time we will run not the RTL simulation, but the gate level simulation. So we'll pick up one of the models, doesn't matter very much, because this is an introductory course. So you say run, and now the machine will launch again the model sim tool, you see, and now is your turn to start a new simulation, a new project. So file, new project. The project name is as usual, so let's change the position of the project. You know the folder. It's going to be as usual, MOOCs 8. This is the project. The name of the project is going to be MOOCs 8, you know, gate level sim in this location, and the default library is going to be work gate level. That's it. So you say OK. That's what you have to click. And now that's the key point. Add existing files. Which ones? Not anymore the pile of PHDL files, but the structure. So you say browse, and what is what you have to browse? Well, the test bench for sure. The test bench is here. You may open and add it. OK. The test bench is the same, but now you may add existing files that when you are going to browse are not in this place, but inside simulation. It is inside simulation, model sim, and you see the BHO. Okay, that is one of them. If you like to see them both, this is one of them, and you may remove the filter. So if you see all the files, the two that you can pick up is the BHO and the BHO SDO, right? Those two are the ones that you go simulating together in this gate level. So you say open and OK, right? So look at this. It's very different from the previous simulation, the functional one. Now you have, I insist on this, it's because it's special. You know, the architecture now is a flat design, the BHO, and that flat design is accompanied by the delay file, and everything has to be, you know, inside the test bench as the unit and the test. So now it's time for compiling all to see if the machine has understood. Okay, successful, so not a problem since now. Okay, so right, if everything is okay, you will launch. I will start the simulation. And that's another tricky thing. What is what you are going to simulate? Well, design. Which design? Not the functional, which was here before, but now the gate level, right? Exactly the MOOCs 8 BHD TST, because this is the name, the extension to the name that the Quartus Prime has added, or the model sim has added to this. So this is the test bench name, you know? Right. And what else? The SDF. Which SDF? Well, let's find it. Add the SDF that you know it is in simulation, model sim, and that one, SDO file, MOOCs _8 _BHD SDO. That's the file that you have to open and place here. But that's not all. You have to add a region, because this file that contains delays is not for everything, but for a single component. Which component? Well, the one that you have in your test bench. So if you browse it, you know, simulation, I mean, if you browse the test bench for a while, this is just to remember the name very well. You get it here, that one, MOOCs 8 test bench. You open it a little bit. So you simply open the file to see this. You see the architecture of the MOOCs 8 is this one. So this is what we are referring to. The component is the MOOCs 8, and this is the entity, I1, right? The entity to which the delays applies. And the MOOCs 8, okay, The MUX8, you know, is the architecture of this entity. And what is this entity? Well, you know, the test bench. So this is the name. Copy. Let's go back to model sim and let's apply to the region, you know, the test bench /I1. That's the point. So you say OK, and now you've got the SDF connected to this design. All right, so it has to work. You say, you click OK, and now the tool will open like that. All right, so very good. And now you can start organizing your wave, or if you have done so before, you can open it, right? So you can add a wave to the system the same way as usual, you know, add to wave all the items in region, or instead, if you like to do it better, or if you've got that recorded from the previous, you know, the setup of the analyzer, the wave, you know, if you've got the setup from the previous functional simulation, you can open it, not to start it from the beginning, but open it, you know. You can open, or you can say open, not like this, but file, import, load macro file, because that was saved as a do, you know, wave do, you know, open. And now, well, in the end, you've got the signals in place, which means that you don't have to just solve any modification, but doesn't matter. Here, now is your turn to run, for example, 800 microsecs. If you do that, you get the waveforms in place. You see? This means that at least it works up to this level, and I mean the level of zoom full, right? If you zoom full, you see the waveforms the same way as you saw them when you did it by means of the functional simulation. So right, so now it's the point. You put the cursor, the time cursor, in some you know, in some transition when you see that the output is going to change. For example, here, that's the transition. And now this time you will go zooming this. Slowly, with the roller of the mouse, you can go zooming this, taking care of not, you know, moving away from the transition. And you see, it is still perfect. You know, the signals changed immediately. But if you go farther and farther away in the zooming idea, you see now you've got this point, this thing. In one cursor, you have the time when the input changes here, let's say that time, and later on you see that the signal gets settled just some nanoseconds later. So let's measure that, adding a new cursor. You see, insert cursor. So you can move the cursor now. This is the beginning, 0 nanoseconds, and from this beginning to here is where you see the settling of the waveforms. You can even zoom that to the full screen. You see this cursor, when the signal changes, for example, selecting from channel 0 to channel 1, and the channel 1 changes the same. So this is where the channel 1, you know, the channel 1 here, is captured this time. You see, now because the channel 0 is 0, the output goes to 0. But look at this, it is not an immediate thing. It takes 9.5 nanoseconds to get the final output. So this is the measurement for this second. You may say that is about 9.5. You see, the signal, first of all, takes a long time to do something. It is like freezed. But then there is a switching here, and in the end it goes 0, and then it goes high again, and finally it goes to the final and permanent value. And this is the measurement that we are liking to generate, not for these moves, but from now on for every single circuit. You see, it's not in some way complicated. It's to go to the right place and get and select the right items through the different menus with all the options correctly stated. Okay, so this is a picture again that you can print and save as an image, and then with your favorite editor you can add comments here. All right, so from this 9.4 or 9.3, 9.5 measurement, you can measure the maximum speed of computing. That to tell you something for this specific transition, if all the transitions will last that time, you know that 9.5 nanoseconds, it's a frequency of 105, you see, 105 megahertz. So this MUX is able to run, you may say later on when we talk about clocks, you can connect this MUX to a larger circuit that runs, for example, with a basic clock, a system clock of 100 megahertz, right? So this is the answer. And to go finishing with this gate level simulation, there is something else here. It's the timing analyzer. So we will still use another tool, because the gate level simulation allows you to put all your attention to a given transition, but you do not know, you know nothing about if this is the worst case scenario. So let the Quartus Prime calculate for us which is going to be the worst case scenario, the longest delay in a given circuit, considering all the thousands of combinations possible, right? So this is something that we will solve now in Quartus Prime itself. It's going to be another tool. Right, so if we are yet again, another time, in Quartus Prime, in our project of the MUX 8, now it's time to start the processing, okay, of a new thing. And this new tool is going to be, you see, it has to be in the list of possible tasks that you can elaborate here, you see. Remember, the test bench has been something that you already have run some time away. Then you continued, you used, the EDA netlist writer to elaborate the translation of the technology view. So now finally, this time you see is the other one, the timing analyzer. So when you click this, the machine starts elaborating a new, this time is going to be a spreadsheet, And how can we go through this? Okay, so by means of the tool, the tool is going to be the timing analyzer. So this is where you are going to see the thing. Now you can go, you see, this is a new window with a lot of tasks and reports. So what we like to see is a specific report. So let's go to the task, the task that we have in mind is that one. You see the many lot of things that you can do here. It's confusing, I know, because that's what I like you to do, and I like you to work even for this simple circuit with a professional tool. And that is the way a professional tool from Intel looks like. And with this tool, if you like, you can invent a very complicated circuit that you can fit in the same FPGA. So you see, from the many reports that you can order to be generated, there is one here that is going to be useful for you. It is called, if I remember, it is called, the data sheet, Yes, this one, the data sheet, the task. So if you click now, the datasheet report, you see you've got what you want, which is the worst case scenario. For example, these people say that from, well, these people, you know, Quartus Prime has elaborated for you all the calculations. And here you are, for example, if you are going to change or switch the channel 0, and you consider the Y as the output, you see, from the channel 0 to the Y output, it takes 8.3 nanoseconds. So, you know, 8.3, okay, is a given value. But is that one the worst case scenario? Well, probably not. You see, down there you have 9. So, of all the values, which is the worst? So, I like you to go rearranging this, you see, in some way. So, the worst case scenario is that one here. You see, 10 nanoseconds. From the selection channel 2 input to the Y output, which is not the Y. By the Y not, you know, there is another gate there, you know. Remember, it was an inverter, a NOT. So this NOT adds some extra delay to the basic output Y. So Y not it has a slightly longer path. So from the S2 to the YL, you've got 10.053. So this is going to fix, you know, in some way, the maximum frequency of operation to 1 divided by 10 nanoseconds, so which is 100 megahertz. Right, guys? So now it's time for you to get a copy of this and annotate that in your report. You know, you have finally answered the objective question, which is specifically how many operations per second can you solve using this, can this MUX8 solve per second? You know, that is 100 million switchings of inputs per second. That's what is the maximum speed of operation. So that's the end of the report, right? And the recording. Thank you.